Hi there. Welcome to Headwaters Science Institute's Lunch with a Scientist. Join us as we talk with working scientists from all over the world as we explore what science research in their career actually looks like. We will host a new scientist every other week and allow them to present their research and follow that up with an open-ended question and answer session. We hope exposure to these professionals will allow students to not only see what type of research is possible, but also see what kinds of careers are accessible, and hopefully we'll have a little bit of fun along the way.
Sometimes we get these amazing sunrises where the shadows from the mountains actually get cast up onto the clouds above. And over the past 15 years, I have spent sort of more and more time studying the sort of snow part of the water cycle. The CSO project is centered essentially on one key research question. Can citizen science have a meaningful impact on our ability to model snow distribution, especially in high mountain environments? So anyone who goes out in the snow, whether it's skiing, snowshoeing, sledding, whatever, can help this effort out.
What's up, everyone? Dan here, Communications Manager with Headwaters Science Institute, and I am thrilled to introduce this encore Lunch with a Science presentation. It's with David Hill. He's an Oregon State professor and a snow researcher. And we felt it particularly relevant right now, considering that we are in the middle of winter and snow is piling up around this country, especially here in California. Don't forget to subscribe and hit the notification bell so you don't miss out on any of our Lunch with a Scientist talks. We're really thrilled about our 2022 lineup. And in fact, we have a shark researcher coming up next week, so you're not going to want to miss that. So subscribe, hit the notification bell, and without further ado, here's David Hill.
Hi, Leah. Thanks for having me. Great to be here.
Yeah, we're so excited to connect. I know that you're not here in California. Where are you talking to us from?
So I'm in Corvallis, Oregon, which is sort of about an hour and a half south of Portland, a little bit north of Eugene, right in the Willamette Valley. And I was just up on one of our amazing volcanoes this past weekend, skiing off the top of Mount Thielsen. Beautiful blue skies, white snow all over the place.
Interesting. Well, we're super fascinated to hear more about snowpack. We teach a lot of snow science programs, and so I'm sure our students will be very grateful to hear how we can use citizen science to study snow. So without further ado, I'll pull in your presentation and I'll let you take it away.
Okay, there we go. I think we're good. I think we've got my first slide up there. So yeah, hi everyone. Thank you very much for tuning in. I hope that you've been to several of these great presentations over the past few months. I know virtual presentations may be less fun than live presentations, but the upside is that they are accessible to locals and non-locals alike. So I'm glad to be able to chime in from Oregon. So I'm glad to be able to contribute, and I'm here to tell you a bit about my work with water and snow. So first of all, I know that we're all sitting at home, but I want you to think about where the closest snow to you is. So these are both pictures from my deck here in Corvallis. I live in a town that doesn't get snow very often. We have a fairly mild climate, but about 80 miles away, we have these incredible 10,000 foot peaks, and these are the Three Sisters in Oregon. And it's really fun to watch them change as winter gives way to spring and summer. And sometimes we get these amazing sunrises where the shadows from the mountains actually get cast up onto the clouds above, which is what you're seeing in the upper left there. So yeah, I've been studying water and how it moves around for about 30 years. And over the past 15 years, I have spent sort of more and more time studying the sort of snow part of the water cycle. I got to admit, part of this is driven by sort of recreational and personal interests. But another part of it is driven by professional necessity. So if I'm interested in stream flow and in water availability in more downstream environments, then I need to be able to understand the distribution and the evolution of snowpack sort of in the higher parts of those watersheds and how that snowpack changes throughout the year. So I love getting out in the snow. I love watching it change, sort of how it changes from area to area and from time to time. So before I get ahead of myself, though, I like to sort of do these talks thinking about like, what is snow good for? You know, why do we care about it? So in a normal year, I might say that snow is good for a snow day at home for my kids, but that doesn't really work if you're schooling from home, much to their disappointment. So one thing is people definitely like to recreate in the snow, and that just absolutely for sure. So a 2018 study of the winter snow sports industries found that in the United States, winter recreation, I'm talking about skiing, snowshoeing, snowmobiling, all of these things, winter recreation added more than $11 billion to the US economy in a single year. And you can see a lot of that is right there in California. Another reason is that snow matters is that it acts as a natural reservoir or a holding area for water. So when precipitation falls all as rain, it runs off of the landscape much more quickly and it can cause flooding. So what you're looking at here is a hydrograph where we have river elevation on the vertical axis, time on the horizontal axis, and that purple line there might show you the hydrograph that we get when it's all rain. Now, when it falls as snow, though, it doesn't run off right away. It may remain in place for several months, and this will reduce peak river flows and help to reduce flooding hazards. So it releases that precipitation more slowly. So the advantage of this snow reservoir are that it is, first of all, it's low impact in the sense that it leaves no permanent imprint on the landscape like a dam might. And also it does not interrupt freely flowing rivers. Third, snowpack also provides habitat for many species. Spring snowmelt helps to keep rivers flowing and it keeps their temperatures cool throughout the spring, and this is very much appreciated by many different fish species. Other animals such as wolverines also depend on snow, but they depend directly on the snowpack itself, not its runoff, for activities such as denning and caching food. All right, so properly motivated, there are really three main things that snow scientists do. We can observe the snow directly to empirically understand how it changes. We can observe the snow remotely, or we can develop theories and computer models to investigate and quantify how, where, and when snow might be changing. And I'll say that most snow scientists operate in more than one of these areas. So for example, if you're going to specialize in computer modeling of snowpack processes, you typically end up out in the field collecting some data that you can use to sort of test if your model is working well. Okay, so that's my general introduction about snow science. What I'd like to do here is to dig a little bit deeper into one recent research project that I co-lead. And this is the Community Snow Observations Project, which has been funded by NASA since 2017. And the CSO project is centered essentially on one key research question. Can citizen science have a meaningful impact on our ability to model snow distribution, especially in high mountain environments? So the key idea here, the key idea of CSO, is that backcountry recreational users and backcountry professionals can provide unique data that we don't get otherwise. And this is because they tend to go to high elevation, far away areas. So anyone who goes out in the snow, whether it's skiing, snowshoeing, sledding, whatever, can help this effort out. So I'm going to start by first reviewing in a bit more detail sort of what sort of snow data prior to CSO has been available for snow scientists to use. Okay, so first, there are a lot of what are called in situ measurements out there. So in situ means that you're actually out in the snow collecting the data directly. So direct measurements of snow commonly include measurements of snow depth or measurements of what's called the snow water equivalent, or SWE. All right, so SWE is just what it sounds like. If you were to take a column of snow, like over on the left, and if you were to melt it, you end up with a column of water which is less in depth. And that is what's called the SWE, the snow water equivalent. So this right here is kind of my skier's interpretation of how SWE changes over the course of a snow year. So at the beginning of the year, it might still be mountain bike season, not a lot of snow yet. And then we have this slow, what's called accumulation phase, where the snowpack builds slowly and steadily throughout December, January, February, March, and so forth. And then this tends to be followed by a much more rapid, what's called ablation, or melt phase. So when the snowpack starts to go, and I will say that peak SWE in most areas is usually at the beginning of April. So once we hit the beginning of April and the snow starts to melt, it really goes in a hurry. Okay, so how do we measure SWE? Well, you can measure SWE with what is called a coring device or a federal sampler. And what this federal sampler is it's basically a series of 1 meter long aluminum tubes that you basically screw together. And you can keep adding them to make your device longer and longer, depending upon the snowpack depth. Now, the lowest piece of this federal sampler has really sharp cutting teeth on it. So you can sort of drive this down into the snowpack and extract the column of snow. And then by weighing this column, you can figure out what the water equivalent is. And by noting the depth of the snow, you can also determine the snow density. Okay, so these measurements are great, but they do take a bit of time and effort. All right, you know, one good measurement can take you 15 or 20 minutes to do, and you have to sort of move from location to location to do this. So there are automated stations, okay, that do this, and they allow us to measure the weight of the snowpack all the time. So these are, you know, these 24/7, they're collecting data on the weight of the snowpack. And what you're looking at here, this sort of flat, fluid-filled bladder that lays on the ground, it's connected to an instrument that measures pressure. And honestly, it's just like a bathroom scale. All it is doing is measuring the weight of what is above it. So as the snowpack accumulates, the weight is sort of increasing, and so on and so forth, increasing the pressure. So these devices are commonly referred to as snow pillows. Don't ask me why, but they're called snow pillows. Now, in the Western United States, we are very fortunate. We have a large network of about 800 snow pillows that continually measure the snow, and these are operated by the Natural Resources Conservation Service. All right, so that's great, and it helps a lot of people plan for how to use the water that we will get when the snow melts in the spring and the summer. And you can go online and you can see in real time how the current snowpack compares, right, to the long-term average for the current day of the year. So this is a snapshot I grabbed from March 11th, so just a couple of days ago. And the color scheme that you're looking at here is sort of showing you how the snowpack compares to what we typically have on this day, March 11th. Anything green and blue is more than normal, white is normal, and anything sort of orange and red is less than normal. So you can see up here in Washington and Oregon, we're having a very good year so far, and in much of the rest of the Western US, things are fairly below average. Okay, so that's in situ snow measurements. We can also measure snow remotely. And what I mean by this is we're not on the ground touching the snow, so we're measuring it from someplace else. Okay, now this can be done using laser light, okay, or what is called LiDAR. And if you haven't heard that term before, it's an acronym for light detection and ranging. The way that LiDAR works is that by timing how long it takes a pulse of laser light to travel from the measurement device down to the snow surface and back, that tells us the distance. So the general idea, if you look at my little sketch here, look at the purple arrow, we know this. So like if we're flying an airplane, we know exactly how high it is above bare ground. And then we do a LiDAR pulse down and it bounces off the snow surface and back. And so we end up knowing through that LiDAR measurement the red arrow. And then we simply subtract to get that blue arrow, which tells us the snowpack depth. So this can be done with planes. This can be done with satellites. So NASA just launched the IceSat-2 satellite, which is super cool. And it can also be done by drones as well. So this little black thing that you see down here is a little toy plane that's just a couple of feet wide. Okay, so one thing to note is that these remote measurements here that I'm talking about, they give us the snow depth. They don't give us SWE. And NASA is very busy at work developing new snow satellite missions that hope to be able to measure or to infer SWE globally, all right, using other methods, which is extremely cool. So remote sensing is amazing. It really is. And if a large swath of the Earth's surface can be surveyed with remote measurements, then you can create these beautifully detailed maps of snow depth. So here in this picture, the Airborne Snow Observatory, or ASO project, was used to create a map of the snow depths in what are called the Maroon Bells in Colorado, a very famous mountain range. So the one downside to airborne LiDAR campaigns, I mean, this is the upside, you get these beautiful pictures. But the downside is that they're very expensive, right? We have complex instrumentation, we have the flight time, all right, for these airplanes, which is very expensive, and so forth. So as a result, these LiDAR surveys of a particular location are fairly infrequent. So maybe we get a beautiful picture like this once a month or once a season. And you have to contrast that with the snow pillows, right? Which, remember I said those are 24/7. Those are measuring data all the time. So these two types of measurements give you very sort of different types of information. So that's a quick review of some of the snow data that we can use to better understand snow processes and to sort of check that our snow models are working well. Okay, so what's the problem? Well, there's a couple. First of all, a lot of snow observations, they come in areas of kind of modest elevation and modest terrain complexity. Those snow pillows that I was talking to you about, those are called snow tell stations. And they tend to be in fairly gentle locations because car access is needed to install them and to maintain them. So what this means is that these snow tell stations are missing the really high elevation, steep areas where the snow depth may be their greatest, right? So that's a big gap in our knowledge. And second, I will say that there are dedicated snow scientists who go out and they try to fill these gaps, and they try to measure the snow themselves in these complicated and these difficult to get to areas. So that's fantastic. But the snow science community is not all that big, and there's a lot of ground to cover. So this brings us back to the idea, the core idea of CSO. Can we harness citizen science in order to improve databases of snow information in high mountain areas? And can we demonstrate that these data have value in terms of improving snowpack models? But before I tell you how we collect our data, I want to say a few things about what do I mean by when I say a model. Okay, it's really just a series of equations or instructions that we program into a computer, and they turn inputs into outputs. That's it. That's what a model is. So we develop models with the goal of reproducing some variable of interest, like stream flow or snow depth or SWE. The reality is that our models are not perfect, and that's because the world is really complicated and there are some processes that we don't fully understand, and so we can't model them. Also, our computer models are limited in terms of how much we can model, and so we can't necessarily model the world at the fine spatial resolution that we want. So our model outputs are often different from reality. They are different from the observations of the world. And this leads to an error, which is the red box in this figure. This error can be really helpful, though. We can use this error to help steer or guide our models back to reality. So the CSO, or the Community Snow Observations Project, is basically this orange box. Can we use grassroots data from the public to help keep our models on track? All right, that's it. Okay, so to keep our models as simple as possible, we ask the public only to measure snow depth, not SWE. Remember I said SWE is a little bit complicated. Depths are easy. You just need a meter stick or a tape measure or something like that. I will say this is one way that you do not want to measure snow depths, okay? So the potential for injury aside, all that we get from an approach like this is knowledge that the depth is greater than one person. All right, so that's not a good measurement. We actually want to know exactly what the depth is. And so if you're in deeper snow, okay, you can, if you're in an area where you only have a foot or two of snow, you can use a meter stick, tape measure, things like that. If you're in deeper snow, a simple meter stick like that won't work. Okay, so one thing that can be used, and one thing that a lot of our participants use, is an avalanche probe. Okay, and this is essentially a meter stick, which is 3 meters long or 10 feet long. And in most locations, all right, that will be enough for you to fully measure the snowpack. This past weekend, when I was up on Mount Thielsen, I was taking measurements, and I did reach a point where even with a 3-meter probe, the snowpack was too deep. All right, but you can get most of the snow measurements that you want with an avalanche probe. Okay, so, but I'm getting ahead of myself again. So what's an avalanche probe, and why would someone have one? It's the avalanches sound dangerous, and they are. And here's the thing, is that if you're going to go into the backcountry, you want to be prepared. Okay, and part of this is basic training and education, learning about where to go, where not to go. Users need to learn how to sort of read the terrain, read the snowpack, understand decision-making in their group. Now, in addition to education, backcountry users need to have basic safety kit with them. So part of this is an avalanche beacon, okay? And I think you guys can see my picture, my image too. So I've got 2 avalanche beacons here, which look just like what you're seeing, okay? And these are transceivers. So right now they're both on, and so they are both sending out radio waves that can be picked up. And if I switch one to search, what's going to happen is you're going to see a number, which is very small because these beacons are quite close to each other. And if I separate them, you hear the sound change, and you also see the number change. Okay, so this is something that people use to find their partner if their partner gets buried in an avalanche. Now, when a buried person has been located as accurately as possible with a beacon search, the next thing that is used is an avalanche probe, right? Which I have one here, and you can also see it on the screen. And it's really just anybody who's camped is probably thinking this just looks like a tent pole, which it kind of is. It's a little bit stronger. Okay. So this avalanche probe is basically used to probe the snow and try and locate a buried person. So the beacon gets you in the neighborhood. The avalanche probe allows you to definitely find the person. And then the third sort of key piece of backcountry safety kit is your shovel, right? Which is what is used to move the snow and get down to a buried person. Okay, so anyone who is out recreating in snowy mountains already has this collection of great citizen science equipment with them, right? Particularly the avalanche probe. It's a perfect device. Okay, so measuring snow depths in the field is great, no problem. Anyone can do it. But a citizen science project is only useful if the data actually get recorded and get submitted by the citizen scientists. And a lot of citizen science projects struggle with this. People go collect data and then they forget about it and it never gets turned in. So having people sort of manually write down measurements of snow depth and then come back home and type up an email and send it in, that's not going to work. So our project acquired the MountainHub app earlier this year. And this app, which started in 2016 as sort of a startup tech company, this allows people to quickly and easily submit time-stamped and geotagged snow depth measurements, as well as other information, okay, directly from the field. So even if you're in a location without cell service, your cell phone knows where you are with its GPS, and it will record the data and allow you to submit it later. So it's very quick, very easy to use. So that's the original idea. And the CSO project started about 3 years ago. How's it going? Well, before we can tell if the results are useful, we have to sort of see if we have some results. I mean, crowdsourcing only works if the crowd shows up. So the CSO project has invested a lot of time in building a community of participants, a global community. And we do this by giving a lot of presentations like this one, by talking at snow and avalanche workshops, by writing stories for ski, snowboard, and avalanche journals, participating in events at ski areas, and so forth. So far, since the beginning of the project, we've had about 3,000 individuals send in over 20,000 data points. And we view this as a huge success in just a few years. And I also want to point out that our project takes sort of an open source, open data approach to science. What this means is that all of our data goes on our website. Anybody can look at it, anybody can explore it, anybody can download it. So if you use the MountainHub app to submit a data point, you'll see your data on our website like the very next day. And you can sort of check out how your measurements compare to the measurements of other people and so forth. Okay, so now remember, our expectation at the beginning of this project was that backcountry users go to sort of more challenging and more interesting locations from a snow point of view than where we have these snow pillow or snow tell stations. So were we correct in that? Well, these are distributions of elevation, slope angle, terrain complexity, and these kinds of things. So let's just kind of take a look here at the upper right. So this is a distribution of slope angle. Okay, so the snow telemetry stations are this cyan line. And if you look at the distribution, you see how they're all down here at like 0 or 10 degrees. So they're on flat surfaces or they're on very mild slopes. Now look at the dark blue line. These are the CSO observations. And if you look at this distribution, you can see that we've got all of these people sending us data from steep mountain areas where the terrain is like 20 to 30 degrees. Right? So this is exactly what we wanted. We wanted to fill a gap, and we wanted to come up with data from a new type of location than what we already have. Okay? Okay, so one last thing I want to sort of show you is like, does this data help? Does this data help snow scientists do a better job? So before showing you those results though, I just want to say a few words about how do we know? How are we going to know if a computer model is working well? Remember, a model is just a series of instructions that takes inputs and creates outputs. A model is trying to reproduce the real world. So if we plot modeled versus observed values of some variable, they should fall on a 1-to-1 line, a 45-degree angle line. That would be the line of perfect agreement. So let's look at a couple of examples of what might happen. We might get something like this. So in this case, we see that the modeled values, they increase as the observed values increase. That's called positive correlation. And that positive correlation is a good thing. But look at these dots. These modeled values are consistently high, and we call that a high bias. So something is not right in our model. We're getting values that are too high, right? So it's not bad. It's got some of the right characteristics, but we have a high bias. This is another possible outcome. Okay, so in this case, the bias is gone. We sort of see that these purple dots are kind of straddling this line of perfect agreement. But I tell you, there's a lot of spread in the data. And that's not great because it means that our model is sometimes way too high and sometimes way too low. So again, not bad, but this is what we call weakly correlated. And then a third possibility could be something like this. Okay, so this is good. We seem to have little bias because the points are evenly distributed on both sides of that line, but they're tightly clustered, right? That means that we've got exactly what we want, a good, strong correlation. Okay, so here we go. In this figure, what you're looking at is our attempt to model the snow. And so on the vertical axis, we have modeled snow. Horizontal axis, we have the observed snow. And all of these different point dots basically mean different days of the year. And when you look at this, you're like, well, it's not so great. He just told me that the data should be on the 1-to-1 line. And if you look at this, our modeled SWE is way too high. So our model's doing something wrong. We have too much snow going on. And part of this has to do with the weather data that is used to force the snow model. Okay, but it's not a super satisfying outcome. What we did is we went back and we reran our computer models by assimilating in the observations that we got from our citizen scientists. If you remember that flow chart, we had that error box and we had the observations. This is the assimilation process. We use the observations to help nudge the model back in the right direction. And so when we do that, this is what we get. And this is astonishing. I mean, all of these data points are right now on this 1-to-1 line. Okay, and I want to make clear, this is a completely grassroots effort. We aren't telling people what to do. People are just going out and collecting snow sort of during their recreational days and so on. And it comes into us and we get this amazing result. Okay, so we let the backcountry users choose how they want to participate. And this approach works really well. So yes, we can absolutely build much better snow models with participation by the public. That was our original research question, and we have convincingly answered it. So now we move on to like, okay, great, who benefits? I mean, anyone who can use information on snow depth, snow distributions, and water storage in a watershed stands to benefit. Okay, we have developed automated methods that allow us to set up and run a high resolution snow model quickly in any location where we have participation, right? The Tahoe area is a good example. We get a fair amount of participation there. So we've created a snow model for that area. This is another example. This is Western Wyoming, okay? Sort of the Teton Range, the Wind Rivers a little bit. And the picture on the left, what you're looking at, the green circles are the locations of snow-tell sites. And then all of the red orange pluses that you see are observations that our team has gotten. And this allows us to build a model like you see on the right. And so this is a snapshot of what the snowpack looks like over the entire Western Wyoming area when we assimilate in this data. So recreational users definitely benefit in terms of knowing where to go to find deep snow. Water agencies benefit. So here in Oregon, it's the Oregon Water Resources Department. They want to know sort of what summer stream flow is going to be like. And our improved snow models help to give them more accurate estimates of summer water availability. Okay, so all of these successes are due to the great collaboration that CSO has. So we have a fantastic crew of snow and data scientists who work on this. And we have an amazing group of regional ambassadors who help us. And these ambassadors, they're mountain guides, they're professional athletes, they're snow scientists, they're educators, they're just people who love snow. And they all help to sort of support, advertise, improve our project, and to help educate the public about the project, about snow science, and about water resources. So finally, I just want to thank the members of the public who have joined this citizen science effort. Okay, all that you need is your phone, an app, some kind of measuring device, some nearby snow, and a few minutes of your time. All right. So again, there is no crowdsourcing without the crowd. And our project looks forward to the future and looks forward to welcoming many new citizen scientists into what we do in this snow season and in future snow seasons. Okay, so thank you very much. I hope that you enjoyed something new. And Leah, I'll throw it back to you.
That's great. Thank you so much, David. I thought that it was particularly fascinating that almost anyone can walk out into the snow and send in their data and have it mean something on the larger scale. Really impressive work.
Yeah, that's it. So while we have kind of this project got started with sort of like, backcountry type skiers and all that, we get a lot of participation from education programs. So we have people that are working with K-12 students and who take them out into the snow and collect data, and it comes to us, and it's all valuable.
Mm-hmm. So I wonder if you could tell us a little bit about how you got into this work. Have you been skiing your whole life, and did that inform your career path?
Yeah, so I grew up in the very flat Chicago suburbs where skiing was not big, but I got exposed to it as kind of a teenager, and then when I went to graduate school, I moved out to the west and went to UC Berkeley, and that really was sort of a formative period in my life where I spent a lot of time in the mountains, looking at water, looking at snow, and yeah, it definitely has affected my career path. And my sort of move into snow has been kind of gradual because I used to spend more of my time studying sort of water closer to the coastal side of things. So I continue to do this, but I've spent a lot of time studying rivers and studying bays and estuaries and so on. And it was through work that I was doing up in Alaska, coastal work in Alaska, where there is very limited information on stream flow. And I started to realize that I'm going to have to start modeling this stuff myself so that I can have the information on the stream flow. And so much of that in Alaska is driven by snow processes. So it was really something where I was trying to study one thing, and it kind of forced me into a new area of study, and it moved me up through the watershed all the way up to the mountains.
Ah, that's fascinating. Higher and higher in elevation, looking at where the water's coming from. That's great. Well, to get into the snowpack, I have a few questions regarding that. My first was, I know that you asked the public not to measure the SWE because it's a more complicated measurement. So they're looking at just the depth. If you find, an area of particular interest where the depth is maybe not what you expect, or you're getting some kind of data from the public, do scientists eventually go and measure more about that snowpack? Do they go out to the area and do more?
You mean like if we saw some unexpected type measurements?
Yeah.
Yeah, we sometimes, so, we get a lot of data that comes into this project, and it's difficult for us to sort of, investigate every sort of data point that comes in, but we do keep an eye out for measurements which strike us as unusual. And, we sometimes have had to sort of reach out to a participant and be like, hey, could you tell us a bit more about this? Like, where exactly did you measure it? We try to give people guidance on sort of how to make a good measurement. And what I mean by this is that in certain areas, think about an area where you have like tree wells, or you have big boulders or logs, or you have really strong sort of wind erosion and deposition. You can end up with, over a very short area, really strong changes in the snowpack. And that can be a little misleading sometimes. Like somebody might use a probe and they make a measurement where the snow is only like half a meter deep. And that's because they hit a large boulder. And in reality, a few feet to the side, the snow might be 2 meters deep. So we
Mm.
encourage people when they're making measurements to sort of seek out kind of a nice clearing where it doesn't look like there's anything unusual going on under the snow. And we also encourage them to take, 3 or 4 measurements in a little bit of a circle, just to give them confidence that they're in an area where the snow depths are pretty reliable and pretty repeatable. And so that's a good way for us to sort of have the public help us do like data quality control by checking their own work, if you will.
Hmm. And so then when you move from there to measuring the water equivalent in the snow, I wonder, does every type of snowpack have the same equivalent of water if it's the same depth?
No, totally not. Absolutely. And that's one of the things that's so interesting is that, so I talked about snow density. So snow density is just a simple ratio of the water equivalent to the snow depth. And so snow density ranges from 0% water to 100% water. And that snow
Hmm.
density varies very strongly geographically. So on the West Coast, we have more of a maritime climate. In the Sierra and the Pacific Northwest, we tend to have really dense snow. So let's say in February, a typical snow density in the Sierra or the Pacific Northwest might be something like 40%. Whereas in a place like Utah or the Rockies, a typical snow density in February might be like 20%, right? Because they have much drier, more of a continental climate there. The snow density also changes, though, as we go through the snow season. So for a fixed location, like the Sierra or the Pacific Northwest or Colorado, pick any one of those locations. And if you were to measure the snow density in December and then February and then April, what you will see is that the snow density steadily increases at that location over the course of the year. And partly that's due to compaction. So when you have a snowpack and you get more snow on top of it and more snow on top of it, that weight compresses the snow, so that's increasing its density. And then also just weather processes, like you can have warming events that sort of do a bit of melt and they make the snow denser. So in the Pacific Northwest, by the time April or May gets here, we have snow densities that can be 60, 70%. It's almost water.
Wow. Well, we certainly need that for the rest of
Yeah.
California, top of the watershed here.
Yep.
And so, speaking of that, of course, the concern really is how much water the snow each year is contributing to the rest of the watershed. So, when you build these models after getting all this data, are you looking to compare places to other places? Or are you looking to compare year to year data for one place to see how the amount of water changes?
Really, the goal is just to kind of provide as complete a picture of the distribution of snow and water sort of geographically. And then, yes, we do run our models over long periods of time. So we can kind of go backwards in time and we can sort of model what's happened over the past 20 years. And that allows us to basically say, for a particular watershed, has there been a change in kind of water storage from year to year? That people have studied that for like point locations. If you think about like these snowtel sites, lots of people have looked at those locations, how had the snow measurements there changed over time. But it's also useful to think about, that's just one point though, so that doesn't tell you everything going on in the watershed. So it is useful to be thinking about trying to model stuff to get the complete picture over an entire watershed.
Mm-hmm. I also wondered about when you assimilate the public observations to kind of do those corrections that you talked about. Does assimilation include just adding the public observations to the model, or do you remove some of the old data points to correct in that way as well?
Well, so what will happen is, so we start our models at the beginning of the water year. So think about like October 1st, and now we are letting the model run, and it's starting to build snowpack. And then what will happen is on a particular day, like February 12th, let's say, at this spot, somebody measures the snow, and we compare what they tell us the snow was on the ground to what the model says the snow is at that location and at that time. And let's say that the model was way too high. So what does that tell us? Well, this person is giving us information that the model is running a little bit too wet. There's too much snow. So from that point forward, what we do is we correct the precipitation to try and bring the snowpack down. And then like 2 weeks later, we might get another measurement from somebody in a different location. And maybe their snow depth is now greater than what the snow model is saying. And so then that tells us that, okay, we have to do another course correction to try and bring the model back up to reality. So it's this kind of constant process moving through time of taking observations. And every time we get one, coming up with a correction that we then use to, from that point forward, try and push the model back in the right direction.
I see. So it's an exciting process throughout the whole year.
Yeah. And, it's because a lot of people will ask us, they're like, well, do you need me, or do you want me to kind of collect data like once a week or whatever? And again, we're not trying to, we want this to be organic. We want people to do whatever they want to do, but we do encourage people. We're like, if you do go to a particular location on a regular basis because it's a favorite hike of yours or a snowshoe of yours, it is really helpful to kind of have repeat measurements in the same general location throughout the snow season. That's really valuable.
Sure. Yeah, I think it's great inspiration, especially for the students that live here in the Tahoe area, as you mentioned, to start working on it and sending you some more data. I think that's great.
Yeah. The Tahoe area is a great place for people to get interested in snow citizen science. In addition to this project, there are some other excellent ones offered through DRI. So there's all kinds of great things that you can do with citizen science and snow down there.
Great. So I want to leave us off on some inspiration for the students who may be watching. If they're passionate about snow, how might they turn that into a career, and what would be your recommendation for their educational path?
So most people come into sort of studying snow through hydrology. So, and you can, hydrology more generally is, of course, just the study of all aspects of the water cycle. But that's a really sort of formative place to sort of learn about the snow part of that. And you can find hydrology in all kinds of programs, so if you're thinking about looking ahead to college, you'll find hydrology offered in natural science programs, so in colleges of science. You'll find hydrology in engineering programs. So it kind of depends on if your interests are more on just the pure science of it or more the applications of it. But that's a great place to look. So, here at our university, all of our students take hydrology in their sophomore year. And that's a great place to start looking.
Great. Well, thank you so much. Of course, David is currently a professor, so if you're inspired, you can always look up David's work. He's been working on snow science for a very long time, and I'm sure that a student would be lucky to be in your class.
Oh, I'm lucky to have him. I always have a great group of students in the hydrology class I teach, and it's great fun. Because so much of it is actually being out in the environment measuring stuff. That's what makes it great fun.
Yeah, absolutely. That hands-on component.
Yep.
Well, David Hill, thank you so much for being here with us. We really, really appreciate it. And I hope you have a great day.
Thank you. I had a great time, and I really appreciated the opportunity. So good luck with your other upcoming talks as well.
Thank you.